Okay, class, good morning. In the previous lecture, we have finished the lecture at this point, that is the number of particles, effective number of particles present in the unit cell, and we have seen the effective number of particle in simple cubic. This is equal to 1 by 8 times of 8, and this is 1. And in BCC, you know, one particle is present just inside at the body center, so contribution is 1, and then plus 1 by 8 times of the 8 particle which are present at the corner, and it comes out to be equal to 2. Okay, then in FCC, you know, 6 particles are present at the face center and 8 particles are present at the corner. So if you find it, then it will be 3 plus 1, that is 4. So the effective number of particle, I will write it, number of particle in face center, number of particle in BCC, body center, face centered cubic, and number of particle in simple cubic. So this is what we have done in the previous lecture. Today we have to see what is coordination number. Coordination number is, see, coordination number. Coordination number is the number of particles which are closest to the atom. You see, this is, I am making simple cubic, or you can make body center cubic. This is the cube, and there are 8 particles present at the corner. You can see here 8 particles are present at the corner. Okay, and 1 particle is present at the center of the cube. This is the body center, which is the intersection point of the body diagonal. Okay class, so you can see this particle is touching these particles which are present at the corner. So the number of particles which are touching it, that is coordination number. Okay, so I can write it, this is the number of particles or atoms or molecules, number of atoms closest to an atom, this is what coordination number. So now we will see, in case of a body center, this is body centered cubic. So here this particle at the center is touched by 8 particles at the corner. So I can say the coordination number of this particle which is at the center, it is 8. Okay class. In the same way, if you see the coordination number of the particles, I am writing it here, and for simple cubic, you will see, for simple cubic, I am making here a cube. This is the cube. This is the cube class. Okay, so we have a particle here at this point. This is the intersection point, and if you make one cube will be behind it, one cube will be below this cube and one will be on this side. You can make the cube like this. This is the another cube. Okay. And if you extend it along negative y direction, this will be the cube, and this is the common face. This is the common face to the both. In the same way, you can make a cube below it, and this is the cube. So here you will make the cube like this. Okay class. So this is shared by 1, 2, 3, and you can make one more cube here. Okay, let me draw it, and it will be like so. You can see this is one more cube, and this corner is shared by 4 cubes. Okay, and 4 cubes are behind it. So the coordination number for this particle will be, you see how many particles are present close to this particle. So 1 is present here. Okay, see in this face 1 is here, and along this 1 is here, and in backward direction 1 is here. Okay, and then 1 is here. So these are in the same plane, and one particle is here on z-axis and one particle is here. So in this way you can see the number of particles touching this corner, that is 6. Okay class. And this is for simple cubic. And if you have FCC, okay, I am making one of the face. This is the face here, and this is the particle. So class C, one particle is present here and another is here. So 4 particles are in the same plane. Now see, what is this distance? This is the face diagonal, and this is cubic. So this side is A, this is A, and this distance is the distance between the particles. This distance is root 2a by 2. You see, the diagonal of the face will be root 2a, and its half is on this side and half is on this side. So this side is root 2a by 2. In the same way, if you see other faces, then these are the faces. Okay, one face, second face on the backward side, third face on this side, and this is the fourth face. So one particle is present here on the front face towards us, and other particle is present on the back face, and one particle is present at the side face. This is yellow colored, and another particle is on this face. So this particle at the face center is touching 4 particles in its own plane, and 4 particles on the face which are below to this face, below this pink face, and 4 particles are above this. You can see these are the faces which are above this face, and in face centered cubic one particle is present at the face. Okay class. So this is the case. This is not at the center of top, this is at the center of this face. Okay, and this is the side face and the front face. This is the front face, and here is the particle. So class, you can see, if you find the distance of this particle which is at the face center, okay, and this particle, it comes out to be root 2a. Okay, so 4 particles are present in its own plane, and 4 particles are present below it, and 4 particles are above it. So in case of face center cubic, this is face center cubic, the number of the coordination number is 12. So here the coordination number Cn, this is equal to 12. Okay, and here the coordination number Cn, this is equal to 8. Okay, and here the coordination number, that is equal to, you will see, this is 6. Okay class, now come to atomic radius. How you will find the atomic radius? Okay, so this is the next thing which we are to see. So atomic radius, okay, and this is for simple cubic, BCC and FCC. Okay class, so firstly come to simple cubic. In simple cubic, you see that particles are present only at the corner. So I am taking one of the face. Okay, and in simple cubic, let me complete it. This is a simple cubic, it is like this. Okay, and I am taking one of the face, this front face. Okay class, so I am talking of this face. Okay, so here in this face 4 particles are at the corner. Okay, and these 4 particles are, let I represent them by circles. For simplicity, I am assuming the particles to be circular, and the particles are like this. Okay, and another particle is present here, and let it is like this. Here is another circle at this corner, and it is like this, and it here we have the particle like this, and this is another particle at the 4th corner, and the particle is again circular. So you will see that this side, let this point is A, this is B, this is C, and this is D. So if we assume in simple cubic the size of the side is A, then what will be the distance AB? AB, this is equal to A. Okay, that is the length of primitive translation vector, and the side we call it lattice constant. And you see here, this is the atom, okay, whose radius is R. Okay, let me take this center point to be O. I am taking the center point O. So here you see, if I assume the crystal is made up of same size of atoms, then the radius of the atoms will be same, and I can write that the radius is equal to AO equal to OB, and this is equal to R. And from geometry you can see this is half of the lattice constant. So I can write here this is equal to A by 2. Okay class, so this is the thing. Okay, now come to BCC. Okay, Now what will happen in case of BCC? Let me complete the graph. Okay, complete the diagram. Okay class, in BCC, firstly see what is the position of the particles and where particles are present, and this is BCC simple cubic, and we have particle here at the corner. Okay class, so one particle is present at the corner and I am making it, this is the center, and this is one of the particle which is represented by this circle. Okay, let this point is A, this point is B, and this point is C. I am taking one more point here, it is D. Okay, and firstly see this face, the bottom face, then we will extend it. I am taking the bottom face, this bottom face. Okay, tell me what is this side. The lattice constant I am taking here, it is to be A. Okay, and this side is again equal to A, and in cubic structure AB and BC, these are perpendicular to each other. So what I can say, that the length of face diagonal, this is the face diagonal AC, AB, this is equal to BC, this is equal to A, and these are perpendicular to each other. So the face diagonal AC, this is equal to root 2 times of A. Okay class, now I will join this point A point to this D point. Okay, then this side will give me the body center, the body diagonal. This side will give me the body diagonal. So this is the body diagonal. Now we are to find the length of this body diagonal. Okay class, and it will be, we will calculate it from this triangle, this side, and then this face diagonal. Okay, you see AC, this is in the plane of base face. Okay, and this side again it is perpendicular here, and what is the length of AC? AC is root 2A. Okay, and now come to this side, this is the side of the cube and its size is A, so it is A. Now you will see this is again a right angle triangle. Okay, and where the longest side is AD, so this is hypotenuse and this is perpendicular and this is the base. So if you find it, AD, this is equal to under the root square of the base plus square of the perpendicular, that is CD. Okay class, and if you solve it, then you will get it root 3 times of A. Clear hai class? Now what is the need to take it? The need is, so class, I am taking this face which is passing through the body diagonal. Okay, and I am rubbing the other faces. Okay, then I will see where the particles are present in this face. Okay, so this is the half part of this section. If I join this, okay class, so this is this one face. Okay, and this is the body diagonal. So one particle is present here. Let me increase the size. One particle is present here. Okay class, and one particle is present at the center, at the body center. So this is another particle. Okay, and one more particle is present at the corner. Another particle is present at the corner, and let this is the particle. Okay class, so you will see that the radius of all particle is same, and this side AD, which is the body diagonal of the cube, that is shared by three atoms. Okay, and you see this distance is equal to diameter of the middle atom, this is equal to radius of the corner atom, this is again equal to radius of the corner atom. So you will see two radius are here. This distance, this is equal to twice of the radius, and this distance, this is equal to the radius of the corner atom, and this distance is again equal to radius of the corner atom. So AD, which is equal to root 3 times of A, this is shared by R plus 2R plus R, 4 radius. So from here I can write that root 3A, this is equal to 4 times of radius. So this is how you can connect the radius of one atom with the size of the cube. Okay, so we have done for BCC. Now come to FCC. Okay class, stop kar diya. So class, now we are to discuss the atomic radius for FCC. So here you will see the atom is present in the middle of the face, and I am taking one of the face. This is the face. Okay class, and this side is A, this side is also A. You are dealing with the cube where all sides are equal to A, and let this point is A, this is B, and this is C, and this is face center. So one particle is present at the center of the face diagonal. So let me draw face diagonal. This is the face diagonal. You will see this is face diagonal, and what is the here AB, this is equal to BC. Okay class, this is the size of the cube, that is A, and AC, this is equal to root 2 times of A. Okay, so now see where the particle are present. This is the center of the face, so one particle is present here. I am putting the particle, this is the particle. Okay, now see another particle is present at this corner, so I am making this particle by yellow color. Okay, and another particle is present at the corner of this, at A corner. So this is another particle. So here again you will see this distance is shared by how many radius? 2 radius here, 1 radius here, and 1 radius here. So AC, I can write that AC, this is equal to 4 radius. Okay, but geometry says that AC is equal to root 2 times of A. So these are equal. So from here you can establish the relation of the radius of the atom with that of the size of the cube, that is A, and from here you see the R, it is equal to A by 2 root 2. Okay class. Okay class, so let me summarize the radius and the coordination numbers associated with different crystal structures. So I am writing here simple cubic, okay, then we have body centered cubic, then we have FCC, okay class, and the coordination number we have discussed, I am writing it Cn, coordination number for simple cubic. In case of simple cubic, this is equal to 6. In case of body center, it is 8. In case of face center, it is 12. And now we see the relation of the radius. So here the radius in case of simple cubic, the radius is equal to a by 2, okay, and here we have the radius equal to root 3a by 4, okay class, and here you have root 2a by 4. So class, this is the end of the lecture, and these properties we will discuss in the coming video lecture. Thank you class for watching.